just like you can. Hello everyone. Let's start with the attendance so we let some more students join us. We have like 2/3 of the class present. So on Monday again it was like not so many students present, not about like 60. So it was Monday, now it's kind of like, I don't know, Friday, I guess. No, students miss more classes. Everyone can get the link work, most of you. You know, sometimes in these questionnaires, I ask some questions, and I told you before, you know, that if I do have questions there, I'm not gonna grade it. But I realized, you know, that in my Chem 101 class, you know, one time I had like 3 questions, and I had like 20 students that they said their link wasn't working. So usually when I have like some questions rather than first name, last name, it's just coincidental, but it's kind of like, that's how it is. Usually, you know, students don't like to answer the questions. Although I tell them I'm not going to grade them. You know, I'm not even like looking who answered what. I just like, you know, see like the percentage, how many students got it right, or, you know, what is the issue the students facing, so I can address them in the class. But it was just something I thought interesting. How many of you are still working on the link? Okay, so I just wait like 1 more minute. I can also open the lecture on my laptop. Okay. So I'm going to start the lecture while, you know, some students still working on the link, and I'm going to just like talk about some logistics of the course, I guess. So, you know, first of all, before being your instructor, I like to be like your mentor, someone that you can, you know, even if you have like questions in general about like what, I don't know, what career path you want to take, or like whether you want to work in industry or, you know, continue grad school. So I want to be a resource for you that you can just, you know, refer to me if you have like questions. And I don't want anyone to be afraid to ask me any questions about the course, you know, or as I said, about like career path or anything. I just want to be approachable and, you know, understanding, so all of you can, you know, refer to me if you have like any questions in general or about the course. And I feel like I have like this communication barrier with some students, and I was talking with some of my students in my other class yesterday that if you have issues with the course, if you're not understanding something, I'm your primary resource. You can reach out to me anytime. If, you know, some students, you know, like email me more often. If you email me, you see that most of the time I answer immediately or like within like few hours. So I try to be really accessible and approachable. So don't be afraid to just reach out to me. Even if you don't know how to name compounds, if you didn't learn, you know, electronegativity or like electron configuration, anything that you don't know, feel free to reach out to me. And I have this policy, you know, in my course, and I communicate that with the students, you know, that as long as you care about the course, you're going to get a good grade, you know. So what that means is that you should reach out to me if you're, if you did not good on like your homework assignments or quizzes, and then your grade is not what you want to be. Reach out to me, and I schedule tutoring sessions with you. I make sure that you know the materials well. Okay? So don't be afraid to reach out to me. So that's that. Everyone's done with the link? Good. Just do it right now.
Thank you. I have a question about like taking exams through CDAR.
Uh-huh. Okay. And I kind of like was looking at the grades on Canvas, and you should be able to see your grades on Canvas too in your grade book. And we have like, some students that they're like on F and D threshold, and some students that they are like lower C. And as you see, like 1/3 of students in general are suffering in this course. And I don't want that to be the case. I try my best to convey the information to you. I know sometimes it's difficult probably to understand what I'm saying, whether like because of language barrier or maybe because of how I try to convey the information, or sometimes maybe you might not be able to read what I'm saying, or you just like you don't understand something and then you let that go, and then you don't understand the thing afterwards. So if you have any difficulty with the course, just reach out to me. This is like still a good point, to try to increase your grades and get A's or B's, But after some point, if you miss so many homeworks or like so many quizzes and then you don't do well on exams, it's just kind of like hard to make up for those. And speaking of makeup, as I mentioned, I'll be having like a makeup quiz 1 and makeup homeworks 1 to 3 today at Renfrew 111. If I can make this work, Renfrew 111, 4 to 6 p.m. for like makeups. Homework 1, homework 2, homework 3, quiz 1. 3, quiz 1. And again, because I should be fair towards all the students, all of you are welcome to take them if you want. And I consider the highest grade. So, but as we, progress with the course, I cannot do that because, for instance, yesterday, instead of preparing for the lecture today, I had to write makeups for my classes. I prepared the lecture like this morning. You know what I mean? And, last semester I had the same issue. Students wanted to see their grades in their grade book, but I was just like doing extra things like makeups and everything, and then they couldn't see their grades, So for me, it's not feasible to just have makeups. So meet the deadlines, and if you cannot meet a specific deadline, email me in advance and let me know. And I told you before, if you're like suffering, you're not doing well, whether emotionally or physically, I don't expect you to do your homework, but you should let me know in advance. Not like after the homework, email me that I wasn't doing well. This is not how it works. For classes, yes.
So for the makeups, will we only be able to like take one of the homeworks, or can we do like as many as we want?
As many as you want. But this is like the only time that I'm providing this opportunity, again, because I want to progress with the lecture, and I cannot just have like makeups all the time, okay? But you are welcome to take any of these, one of them, two of them, three of them, or like all of them, and I consider the highest grade. Any questions about that? Yes?
What homeworks does quiz 1 cover again? Is it all 3 homeworks or?
So quiz 1 would be the materials that we covered before I posted quiz 1. So in short, it would be like naming alkanes and cycloalkanes and anything we learned before that. Or like anything that we learned in this course except intermolecular forces, boiling points, physical properties, things that we discussed last session. But yeah. Any other questions? Good. Okay. So that being said, if you are one of the students that they are like having lower C and D and Fs, and remember these, online versions of the tests, they were open book, open notes, but today the makeup would be closed book, because as I told you, I expect you all to know the answers after you're done with the quizzes and I post the solutions, so I expect you to study them and learn them for your exams. But if you're one of these students that they're not doing well and you don't want to change the amount of the time that you devote to study, it's highly you're not going to do well in this course. And although I don't want to encourage anyone to drop my course, I love to have all of you in my class and help you succeed. But if you cannot devote time to study, you have like until next Friday to drop the course. And I don't want to, lower your GPA with my course. I try my best, to provide so many opportunities for you to increase your grades. I provide tutoring. You have tutoring sessions like Thursday 6 to 8, right, with Sean. And I told you if you cannot go to his sessions, you can just go to any tutor and ask them to email me, and I give you 5 points out of 1,000. Basically 0.5 out of your 100 in this course. 5 out of 1,000. So technically, if one of your quizzes you got like 10 out, or like one of your homeworks you got 10 out of 20, you can go to two tutoring sessions and make up for that. So I feel like that's really awesome, to be honest. If you just go to so many tutoring sessions, you can technically increase your grade 1 letter grade. And I think that's a fair deal. But so far, I had like 2 students going to tutoring sessions. And one of them has the highest score in this class. So don't feel like, if you go to tutoring, it means that you're suffering in this course or your grade is low. Most of the time, the students that go to tutoring, they end up with like higher grades. Anyway, so this is that. Any question about this? Good? Okay. So now, if you guys don't have any questions about like logistics, rules, and all the things that I talked about, I'm going to continue the lecture. And again, I asked you guys to buy the book, and you have like the e-text in Cengage website or like bookstore, Vandal bookstore, and it's kind of like, I think in bookstore is like $46. In Cengage website is like $39.99. But I require you guys to have the textbook, because if I just teach you and then if you just listen to the lectures and then look at the PowerPoints and don't study the book, probably you cannot do as well in this course. You should have the textbook, okay? And if you have difficulty getting the textbook, just email me. I guide you or like link you to the publisher so you can have the book. And again, I told my students in like all my classes that if you have like financial difficulty, or if you just don't want to spend the money on the book, you think it's not needed, or you really don't want to, just come talk with me. I reimburse you. And as I said, I encourage you, if you have the money, just like buy the book, because I'm not like that rich myself. But I don't want anyone suffer in this class because they didn't want to buy the book. Okay? Any questions? Okay. So now I really go, talk about just like the lecture. So can anyone tell me what were isomers in general? If I say like these 2 molecules are isomers, what do I mean?
Same amount of atoms, but just rearranged differently.
Exactly. So we have like the same elements, the same number of atoms, and same molecular formulas, but we have like different structures. So if I just write the chemical formula of 2 molecules that are isomers, just by looking at the chemical formulas, you may not know that they are isomers, or you cannot know because the molecular formulas are the same. but they have different structures. And we have like two different, or like, if we just, consider this part of the categorizing isomers, we have like two different kinds. Or in general, if we consider these ones here, we have like three different types of isomers. The first one is a structural or constitutional. Now, I don't like to memorize names myself, but sometimes we have to. So the first type is like constitutional or structural. And we talked about that. I remember I started the lecture, very first session, with these types of isomers. Remember that I had them like in the board and I was showing them, So it means that they have like different bonding pattern, right? And if I just like look at your book, very first page, I can tell you what were the examples. I guess here, I apologize to people that are at home, but I'm going to tell them, because I'm still recording, that it's like page 1 of your book that I'm showing in the class, And when I was like preparing for the lecture, I had like these two structures written here. So one of them was like methyl butyrate, the other like propyl acetate. You see that both of them have like C5H10O2. If you just look at like the molecular formulas, can you say they are like different compounds? You cannot, right? But if you look at the structures here, you see that structures are different. Okay? So that was the first type. Okay? That we talked about that before in this class too. The second types are like, stereoisomers. So they have like the same bonding pattern. They're not like structural. They also, they have the same bonding pattern as well. But when you look at the geometry, when you look at the 3D structure, you see that they are different. What I mean is that those are like, stereoisomers. Right? Are you with me? So one was like conformational, the other configurational. But what is the difference? So both of them, both these categories, they have the same bonding pattern. And if we look at them, look at the 3D structure of the molecules, in that way, they won't be different. But one type, conformational, we can convert the isomers to one another by single bond rotation. It means that if you have the 3D structure of the molecule, and if you rotate it around a single bond, you can get the other structure. But for configurational isomers, if you have the 3D structure and then you rotate around, any of the bonds, you cannot get the other structure. So they're not interconvertible by single bond rotation. Does that make sense? So isomers in general, they have like the same chemical formula, different structural formulas, okay? And if they have like different bonding pattern, we call them structural or constitutional. If they have the same bonding pattern, but when we stereoisomers, and they can be conformational or configurational. Any questions? So I came up with this policy in my class that if I see someone is not paying attention or like they're just talking or laughing, I ask them questions, and usually students just don't talk anymore because they don't want me to ask them questions. So I'm going to do that, from now on. If I see someone, just like not paying attention or being distracting to other students, I'm going to ask you questions. So just to give you guys a heads up. Any questions so far about this? Good. Guys, here I just like use red so much now. So we talked about this. So remember, conformational is the one that we can just rotate the molecule around like a single bond and get the other structure. But for configurational, we cannot convert them to one another in the space, okay? Configurational isomers, okay, that we cannot rotate them around the bond and get the other structure. Does that make sense? So this can be also like cis trans. Let's go to the next lecture, next slide, sorry. So they have like the same constitution. Remember the first type of isomers were like constitutional isomers or like structurals. They have the same constitution. It means that atoms are bonded in the same order, but atoms are located in different places in the space. And we also know conformational. This is the conformational. You see the definitions are the same. And both of had them in a space, or if they are located in different places in a space, we call them, we already talked about conformation. And other type, conformational isomers, and here you have an example of ethane molecule. And I posted a video and I asked you guys to watch that. Again, I'll ask you to go back to that video and watch it. And in general, if you have any questions about any part of our course, feel free to just like Google it and then go to like, you know, legit websites and then kind of like learn more about the concept. You know, I remember when I was going to school, if we didn't know something, we should have, you know, bought a book or like borrowed a book from library or find someone that they knew, you know. I mean, the information wasn't this much available as it is now. You know, if you just like Google conformational isomers, you see like tons of websites with information. So even, you know, if something's not clear and you insist not asking me, just feel free to just like Google information, you know. And for instance, Khan Academy is one of the websites that usually the information are like legit, and then they source some you know, articles that they use, or they say where they got that from. Anyway, so again, you know, study the book, and I just like, you know, emphasize this enough. And for some of the concepts that we go through, I just, you know, I don't go through all the materials. And when you're reading the book, if you see something that I didn't talk about it at all in the class, you know, you don't have to stress about it so much. You know, kind of like conformational isomers, your book talks about, you know, in much more details about those, but in the exam, I asked you, you know, however much I talk about in the class. Does that make sense? Okay. So we have like different conformational isomers for ethane. So we have like two extremes. What that means is that, you know, you have like these different structures here, these isomers, and one of them, you know, we have like, you know, eclipse, and, you know, staggered, that you're, where is it? We have like the, so here you have like different configurations, but, you know, I'm not going to ask you these different names and all that, but I asked you, you know, staggered and eclipsed, and like which one has like highest energy, lowest energy, which one is most stable. So the one with lowest energy is more stable. And I asked you which one, you know, we can find in like room temperature. Does that make sense? Just the things that I mentioned. And again, you know, these like, when you rotate these molecules in like around like different bonds, like if you rotate them, you can just get like the other structure, but I'm not going to emphasize on that in this course, that if we rotate it in like different angle, which structure we get, or all that, those ones, you know, you're welcome to read the book and learn them and ask me if you have any questions, but I'm not going to cover them. So as long as you learn like what conformational isomers are and what are staggered and eclipsed isomers for ethane, you should be good. Any questions? Good? Two different, you know, isomers. And they can be structures in between. As we said, it's kind of like when you rotate the molecule around like each of the bonds, you can get another, configuration. So we have like these two, one of the, most popular, if you will, the isomers of ethane. We call one of them staggered, the other eclipse. And this structure here, staggered, it has like lowest potential energy. And in general, in nature, atoms, molecules, all matter, everything, they want to have the lowest energy possible. This is just how nature works, If two things, and this is how molecules will bond together, And if you take like some more advanced courses on like molecular modeling, that you want to model different molecules, what those softwares do, they put like molecules in like different configurations, different bond length, different distances from each other, and the software calculates all the energies associated with different configuration, and it calculates the energies, and the one that is lowest is the most stable configuration. Does that make sense? Kind of. So just remember, we want to have the lowest energy possible. So for this structure here, staggered, we have like the lowest energy, but for eclipse, we have like highest energy. For that matter, almost we don't see eclipse isomer, of ethane in like room temperature, because it's not stable, because it has really high energy. Does that make sense what I'm saying? Okay, so so here again, you have like those, different structures, and eclipsed and staggered. And again, it's kind of like paraphrasing what we said before, and here again it explains why eclipse structure is not that stable. And that is, one explanation would be because of like it has like really high energy. But why it does have it has like really high energy, it's because of steric interactions. And what is a steric, or what are steric interactions? They are repulsion caused by two atoms that are like too close in space. So their valence shell electrons repel each other. If you have like two atoms, right, and then you get them so close to each other, their valence shell electrons, non-bonding electrons, they repel each other because they are like negative, right? Electrons have like negative charge, so it's not stable. So for that matter, they have like really high energy. So that's why we don't have eclipse structure. And here again, your book has like the hydrogen distance in eclipse is like 2.36 angstrom, and the same distance, hydrogen distance in staggered is like 2.54. So you see that in eclipse, the atoms hydrogen distance is much lower, because atoms are like close with each other, and we have like steric interaction, so we have repulsion between non-bonding electrons, and that's why it is unstable. These things make sense? Good. Any questions? So don't be afraid, to ask me questions. I had one student in my other class that was coming to my office hours and was asking me questions, and then they were telling me that, am I the only student that I'm like struggling, I don't know the answer? I was like, no, you're not. I have like half a class that they not following me, but most of the time students don't want to ask questions, so don't be afraid to ask questions. So if I wouldn't study these things, I wouldn't know what are like conformational isomers either. You know what I mean? So if you don't understand some concept, it doesn't mean that you're doing something wrong, probably I'm not explaining well. So just ask me anytime you have any questions, okay? So if I tell you, give you these two numbers, 2.36 angstrom and then 2.54 angstrom, I'm gonna do this for a second. So if I give you these two numbers and I say which one is eclipsed, which one is staggered, which one is staggered, I call this 1, 2. So which one is staggered? So staggered. Okay. So why? Yes. So the greater distance or like longer distance causes to what?
Lower energy, be more stable.
Exactly, lower energy, so being more stable. Does that make sense? Okay. So I may give you like some numbers in the exam, so from like some other isomers, but they ask you which one is more stable. Does that make sense? So you should, learn the concepts. Okay? So now I'm just kind of like talking about like the names. Geometric isomers or configurational isomers, they have also really similar definition. Subset of, there are molecules which have the same chemical formula. The atoms are bonded in the same order, but located in different positions in space. You see, it's almost the same. Okay, let me go to the next slide. We also talked about geometric isomers or configurational. And now, now we want to talk about, cis trans isomers, which are basically geometric isomerism. So it's kind of like the other name. Here I have like the definitions, and then in the next slide I have an example. So these isomers of cycloalkanes are a type of stereoisomers in which substituents are whether on the same side, that we call them cis, or on the opposite side trans of the ring. So in general, consider this example, and as I said, anything that I have that I don't cite is from your book. But if I have a citation, I got it from that website. So you see, here we have like methyl substituents, right? Or branches, or like functional groups, right? All of these are, the same meaning. So we have like these branches or like substituents. So, and again, remember, these are like 3D structures, right? So if we had like the molecule, these CH3, these methyl groups are like, towards the ceiling. You know what I mean? It's kind of like, it's like 3D structure. That's why this is how we show them. So this ring itself is on the plane, kind of like a straight plane, but these methyl groups are like towards up or towards down, depending on where they are. Does that make sense? So these are like 3D structures when we talk about like, cis-trans isomers. So if they are on the same side, we call them cis. If they are, in the opposite side, we call them trans. So if I consider like this, piece of paper, if I have one methyl group here and the other methyl group down, it would be trans. If I have both of them on this side, on one side of the ring, it would be cis. Does that make sense? And if I rotate this molecule to around any bond, I cannot get the other one. We cannot convert them. They are not interconvertible. So that's why we call them geometric isomers. Any questions? Yes?
So if you were to have like both of them on the left side, but one of them on the inside, one on the outside, would that be
So as long as they're like the opposite side of the ring, they would be trans.
Okay, but if they're like, okay, so like inside versus outside?
Uh-huh.
Okay.
Yes. Great question. Any other questions? Good? We had like, 1,2-dimethyl cyclopentane. So it might be, let me see. Pentane. Okay. So here, here we have like 1,2-dimethyl cyclohexane. So kind of like another example that we have like cis and trans structures, So kind of like you have like CH3 here, CH3 here, or you have them here, CH3, CH3. You see, it's kind of like sometimes it's like difficult to see when you have it like 3D structures written on the, paper. So it took me like some time to recognize like, where is like second CH3 here. But for the trans, it's kind of like more obvious, right? Because if you consider this ring here, you see like one CH3 here, the other here is like more straightforward. But for here, it's kind of like harder to see, But for trans, it's like more obvious. Any questions? Yes.
So it says that it's hexane, but why wouldn't it be butane?
Huh. That's a great question. Yeah. Yeah, that might be a typo actually. Yeah, great catch. Any other question? What was the question?
So if they're both outside, is that cis? Or is that trans?
If they are both on one side, it's cis. If one is up, one is down, that would be trans. I may also be able to use another pen I have. So here, this would be trans, but this would be cis if both are on the same side. Does that make sense? And great catch on this. I'll check on this slide. Yeah, this is like one of the slides of the publisher. So I just was like, I didn't pay attention to the, I just assumed it is correct. So I look at this and then, update you next class. Okay? Great catch. Any other questions? Good. And again, remember, these structures cannot interconvert without breaking a carbon-carbon bond. We cannot get cis from trans. And what we mean is that if we have the 3D structure and then we rotate it in space, we cannot get the other structure if they are geometric isomers or like cis-trans. Good? Okay, so now I'm going to start talking about chemical reactions of alkanes. And again, I try to include as much as information as possible in the slides, but again, you need to read the book. So all of the bonds of alkanes, there are single. So this is how we named alkanes, right? They have like single bonds, and they are covalent, right? Because they share electrons, and they are nonpolar. Can anyone tell me what they are nonpolar?
Carbon and hydrogen, they have similar electronegativities.
Exactly, carbon and hydrogen have like similar electronegativity, right? So for that matter, the bonds would be nonpolar. And this is something that I emphasize a lot, and I'm, keep emphasizing in this course. So alkanes are relatively inert. And inert means that they don't want to participate in reactions, okay? And they're basically the same thing that we said, but now we kind of name other, chemicals. So alkanes ordinarily, they don't react with acid, bases, oxidizing, or reducing agents. So they're inert. But we have two types of reactions that alkanes participate in. So, before I explain about that, because alkanes are inert, most of the time in laboratories we use alkanes as solvents. And one example would be solvents for extraction or like crystallization, reactions. Or like in general, sorry, I guess I shouldn't say, I mean we can have like, extraction or crystallization reactions too, but most of the times, or we have like examples that, crystallization or like extraction or like just like physical changes. But in general, we can use these solvents for, extraction and crystallizations, so we need solvents to do extraction or crystallization. And we use them for carrying out chemical reactions of other substances. So we have like sometimes, we use them for like physical changes, as I said, for like extraction or crystallization. Sometimes we're carrying out reactions and we need to have a solvent to carry out that specific reactions. Because they are inert, they don't participate in the reaction, we have alkanes, as solvents because they are inert. But as I mentioned before this bullet point, I guess, alkanes do react with some reagents such as molecular oxygen and the halogens. And this is what those types of reactions that we're going to cover, in the next slides. Yes?
So when it says alkanes reacts with like molecular oxygen and halogens, for the halogens, is it like just like the pure like fluorine or something like that, or would it be like
Back to where I was. Okay. So can anyone tell me, we want to talk about oxidation reduction reactions and combustion reactions. So can anyone tell me what is or what are combustion reactions? Can anyone remember from previous chemistry courses that you had? Anyone? Yes? What is it? Exactly. So combustion reactions, they are highly exothermic, right? They release heat or release energy. But what should I have for combustion reactions to occur? Oxygen, right? So in general, the traditional definition of combustion reaction is that we have like a substance and they react with molecular oxygen, right? And they release or they produce oxygen containing species and plus lots of energy. So that would be like definition of combustion reactions, okay? And can anyone remember what is oxidation reduction reactions?
Oxidation loses electrons and reduction gains them.
Oxidation loses electrons, yes. So in general, we have electron transfer in oxidation reduction reactions, right? And that is like the general definition. And we said that alkanes are not reactive, they're inert, but we burn alkanes so much, right? We have like, we use them as a fuel, or whether in our, cars or like in houses, right? We have like, we use butane and burn it, or like propane, depending on what type of alkanes we're using. So in general, and again, I know I include the bullet points because I'm going to ask you in your, quizzes, homeworks, exams. So the most important use of alkanes is as fuel, and with excess oxygen, alkanes burn to form carbon dioxide and water, right? Because alkanes, they have carbon and hydrogen in their structures, they release carbon dioxide and hydrogen. Does that make sense? Because we have C and H, so when we react with O, we get like CO2 and H2O, right? We have like C and H, so if we react them with oxygen, we'll be having like compounds that have like carbon, oxygen, and hydrogen oxygen. So carbon dioxide and water. The reactions involve considerable heat. The reactions are exothermic. So if I tell you that if we burn methane, the reaction would be endothermic, is it true or false? False. The reaction would be exothermic because it releases heat, right?
With
Okay. Okay, and here we have like an example of like combustion reaction, methane plus oxygen gives CO2 plus H3O and heat. And even here for like butane, right? It's kind of like the same. And if I just like give you these reactions and I ask you which one gives me more heat, even if you don't know the numbers, which one do you think gives me more heat? The second one. Is it obvious why?
It's got more stuff
More
inside.
reacted.
So what did you say?
It has more like stuff to burn.
Yes. Yes. So we have like here, we have like, just 1 carbon and 4 hydrogen. Here we have like 4 carbon and like 10 oxygen because we have like more fuel, or like the molecule is heavier. Here we'll be having like more heat as well. Does that make sense? Is it like, if I like burn a piece of wood or if I burn a tree, right? The second one would release more heat, okay? And combustion reactions are the basis for the use of hydrocarbons for heat. Natural, I guess this has here is extra, natural and heating oil. And for power, like gasoline. So remember that these are like, we most of the time, we get the power or like the heat from like burning or combusting hydrocarbons. And also one thing that is really important that you should always remember, that in any reaction, including combustion reactions, if I have like methane gas here in a cylinder, does it burn by itself? Why doesn't it burn? Isn't it a fuel? Yes?
Because it needs to be combined with the oxygen.
It should be combined with the oxygen, but even if I just like open the methane tank here and it just like distributes in the room.
It has to be like a spark.
Exactly, we need to have a spark, right? And that is something that in chemistry we call so any reaction that we have, we should provide an activation energy. Does any of you remember this? And like for some reason I just draw it really small. So if I have something like this, any of you remember these types of like depicting like chemical reactions in a diagram? Does it seem familiar? So the amount of energy that is needed to initiate a reaction, we call that activation energy. So in general, if most of the reactions, they have like some considerable amount of, they need like all reactions rather, they need some initiation. We need to give some energy. If I have like piece of wood here, we have like oxygen too, right? But wood doesn't automatically just burn, right? Or the same thing with methane, propane, or like all fuels. But some of them have like lower activation energy. So that's why if you have a tank of pure hydrogen, it's much more, volatile and dangerous than ethanol, for instance. So that's why, this is like the controversy about like hydrogen-based fuel cells, that they carry pure hydrogen. So if we have like just gasoline in our car and we have like accident, maybe nothing happens, or like it won't be an explosion. But if we carry pure hydrogen and then we have a minor accident, it might just like we have a catastrophic accident, because hydrogen is much more volatile and is like the activation energy for hydrogen to burn is like much lower. Does that make sense? So to just like finish this sentence, an initiation step is required, usually ignition by a spark or flame. Once initiated, the reaction proceeds spontaneously and exothermically. I guess I just like continue with the lecture next session. And I'm going to post quiz 1 during the weekend. The reason that I didn't post it is that I wanted to, include more materials. And if anyone, okay. Great question, and to answer, but great that since I have this slide here, I just show it here. So, as well. Oops, next detail, like so most of the time halogens, we have them as like molecular halogens, but in some instances you can have like the atoms as well, but most of the time when we reacting substances with each other, we have like how they are in nature. Does that make sense? And we're going to talk about them in more. Didn't mean to do that. So it can be like Cl2. We can have instances that